In this video, I'm going to go over the problems in your worksheet packet in case you had any questions on these. So I'm just making out the key for you here. Okay, for this first problem, you need to do by parts on it. Cannot do use of, gotta do by parts. This is a good candidate for the tabular method. I'm going to come over here, u and dv. So 4x cubed. Under the u, take the derivative until you get to 0. So 12x squared, 24x, 24, and 0. Under dv, you put everything else. And then remember that we're integrating this side. So the integral of cosine of 2x is 1/2 sine of 2x. Integral of sine of 2x is -1/4 cosine 2x. Integral of that will be a -1/8 sine of 2x. And the integral of this would be 1/16 cosine of 2x. And now we multiply diagonally. And then we switch the signs here. Keep the first one positive and then change the next one. Keep, change. Okay. So we can come down here and write our answer. So this will be a 4 times 1/2. So 2x cubed sine of 2x. This will be another positive. 3x squared cosine of 2x. This one will be -3x sine of 2x, and then a -24/16, or 3/2 cosine of 2x plus c. In this one, we need to come off to the side and do our little by parts decomposition on it, because I see that the bottom can be factored, right? Bottom can be factored, so I'm going to come over here. X plus 13, and then this factors into x plus 3, x minus 2, a over x plus 3, b over x minus 2. Multiply both sides by that common denominator, and we get x plus 13 is a times x minus 2 plus b times x plus 3. Begin by letting x be 2. We'll get 15 is equal to 5b, which means b is 3. If we let x be -3, we'll have 10 is equal to -5a, so a is a -2. So back to our problem, our integral, I'm replacing that fraction with -2 over x plus 3 plus 3 over x minus 2 dx. Two little natural logs, -2 natural log x plus 3 plus 3 natural log x minus 2, and we're evaluating that from -2 to 1. So we'll have, when we put 1 in for x, we'll have -2 natural log of 4 plus 3 natural log of the absolute value of -1 is just 1, right? Minus, okay, put -2 in for x, we'll have -2 natural log of 1 plus 3 natural log of 4. That would be a safe stop spot. In this case, if for the year 2020, I would totally leave it like that. That's 0 though, that's 0. So this would be -2 natural log 4 minus 3 natural log 4, which would be -5 natural log 4. That would be fine. You might see it like that. Okay? As a multiple choice. Okay, for this one, I see 3 over cosecant squared. I want to change that to the 3 I'm just going to pull out. Cosecant squared of 5x is 1 over sine squared of 5x, so this is just sine squared of 5x. And I see that sine squared, and I want to change it to 1/2 minus 1/2 cosine of 10x. I'm using the identity for the double angle identity for cosine. And now we have something that's very easy to integrate. This will be 1/2 x minus, the antiderivative here would be 1/20th sine of 10x. That's it. Okay, for number 4, I see a little u sub. If I let u be the bottom, du is going to have an x in it. So that's what I'm going to do. U is x squared minus 1. Du is 2x dx. 1/2 du is x dx. So I'm replacing just x dx with 1/2 du. And on the bottom, I have just a u. So 1/2 times 4 is 2. I'm going to take that outside the integral. And then I have 1 over u du. Do not put the 2 and the 3 on the boundaries, because you have u now. You don't want to use x boundaries for a u expression. So change these. So if we put 3 in for x, we get 9 minus 1, which is 8. So our new upper boundary is an 8. If you put 2 in for x, we get 4 minus 1, which is 3. So our new lower boundary is a 3. So we have 2 times natural log of u going from 3 to 8. That's 2 natural log 8 minus 2 natural log 3, right? Safe stop, that's fine. You might see this as 2 natural log of 8/3, which is also natural log of 64/9. You could see that different ways. If it was multiple choice, we'd have to play around with that to get it to match one of the choices. Okay, number 5. In this problem, I need to use biparts. Algebraic times an inverse trig function, and I need to let u be that inverse trig function. Du, the derivative of arctan of just a plain x, is 1 over x squared plus 1. Let dv be your x dx. So v will be the integral, so 1/2 x squared. uv minus the integral of v du. Right? This 1/2 I'm going to pull outside. And then I'll have x squared over x squared plus 1 dx. Well, x squared over x squared plus 1, how do we integrate that? Well, the powers are the same, so I know what to do. If the powers are the same, I come over and I divide. You have to. So I'm dividing x squared plus 1 into x squared, and I cannot use synthetic division this time because of the x squared on the bottom. Okay, x squared, I multiply by 1 to get x squared. 1 times x squared plus 1 is x squared plus 1, and I'm subtracting these two, right? X squared minus x squared is 0. 0 minus 1 is a -1. So this is my remainder. So with that remainder, I put that on top of the x squared plus 1, right? You can pull that minus out front if you want. Okay, so over here I have, just rewriting this, arctan. Okay, I'm going to put this quotient in here. So 1 minus 1 over x squared plus 1. And now I can take the antiderivative of each of these pieces. Okay, the antiderivative of 1 with respect to x is x. The antiderivative of this is arctan. Just your most basic arctan. And that's it. We're done. Okay. Number 6. Got a little algebraic times an e function, transcendental, and I cannot do u sub. If I let u be the exponent, I'm not going to have any x's left, so I need to do something with this. So it definitely is a by parts problem, right? Definitely by parts. U and dv, this is a good one to use the column on. So for the u, I'm going to let u be the 4x squared. Take the derivative until you get to 0. Didn't take too long. For dv, I'll let that be e to the negative x over 2 dx. And remember, we're integrating. So the integral of this is going to be e to the negative x over 2. And now the derivative of that would be a negative 1/2. So we need to undo a negative 1/2, and I'll make it a negative 2. When I do that, I'm just doing a little u sub in my head. Make it quick. Here we'll have e to the negative x over 2 again, and then we're multiplying by another negative 2, and it'll make that a 4. And then once more, and then multiply by negative 2 again, we have negative 8. Multiply diagonally, watch your signs, and then we can come and write the expression here. So, and I just noticed I have boundaries, so I need to make sure I keep my boundaries there. So negative 8x squared e to the negative x over 2 minus 32x e to the negative x over 2 minus 64 e to the negative x over 2. And we're evaluating that from 0 to 1. So if we put 1 in for x, we'll have negative 8 e to the negative 1/2 minus 32 e to the negative 1/2 minus 64 e to the negative 1/2. I should have factored out the e to the negative x over 2, but I didn't. If we put 0 in, this term will be 0, this term will be 0. This term will not be 0 because e to the 0 is 1. So we'll have another negative 64 here, like that. Okay? All right, next up. For this problem, I know I cannot do by parts because of this x squared right here. Cannot do by parts. This is just a u sub. Let u be the 2x squared. du is 4x dx. So 1/4 du is x dx. So I'm replacing x dx with 1/4 du. And then this is now a u, right? So we have 1/4 integral cosine u du, which is 1/4 sine u plus c. Replace your u with your x expression there. That's it. Okay, number 8. All right, this e on the bottom is going to cause us trouble, right? So I need an e on top, and there's only one way to get an e on top, and that's to multiply top and bottom by an e expression. But I want to be careful what I multiply by because I don't want to do too much with this. I want to kind of, anyway, what I'm going to do here is I'm going to multiply top and bottom by e to the negative x. Why? Because it'll get me an e on top, and it'll change this to have an e with it, and this will no longer have an e with it. So I'm doing just enough to make it work for myself. So we'll have 4e to the negative x over 3e to the negative x plus 2. Because e to the x times e to the negative x is 1. Now I can do a u sub. U is the entire denominator. So du is negative 3 e to the negative x dx. So negative 1/3 du is e to the negative x dx. So I'm replacing e to the negative x dx with negative 1/3 du, and on the bottom I just have a u. So I'm going to pull out that negative 4/3, and then I just have 1 over u du. And we know how to integrate that. Natural log of u plus c. Don't have to have those absolute values because that argument will always be positive. Okay, little improper integral. We do have a vertical asymptote at 0, at x equals 0, but 0 is not in our boundary, so we don't have to worry about that. But it is going up to infinity, so that's going to make this improper. I'm thinking, in my head, I'm thinking of this as 3x to negative 3. That's what I'm thinking of. So this will be, I'm going to leave a space for that limit, right? This will be x to the negative 2, because you add 1 to the power, divide by negative 2. And we're going from 2 to infinity, but we don't write that infinity, because infinity is not a number. You can only write numbers there. Okay, before you start plugging in, write this x to the negative 2, write it back as a fraction, okay? It'll help you. And this negative 3/2 I'm just going to take out. Okay. I like it that way better. Okay. So we have negative 3/2 times, put b in for x, and let b go to infinity. B in for x, b goes to infinity, we'll have 1 over a huge number, which is 0. That first, when we put b in, we get 0. Minus, now we put 2 in, we get 1/4. There's your safe stop answer. This would be 3/8. Okay, for this one, vertical asymptote at x equals negative 1, not a problem here for these boundaries, but we do have that infinity. So for this one, the antiderivative is just natural log x plus 1. I want to take it from 1 to infinity. So for this time, we put b in for x, let b go to infinity. We have natural log of something going to infinity. This is going to infinity. Minus, and then when you put 1 in for x, we just get natural log of 2. Well, this is an unbounded number, so this integral diverges. And by the way, if we think of this as a series, this will behave like the series behaves. And that compares with the diverging harmonic series, so that diverges as well. So those guys together, right? Okay, next up, number 11. Why is this here? Because this is also an improper integral, because we have a vertical asymptote at x equals 1/2, and that is our boundary. So one of the boundaries is an asymptote. Okay, we're going to go ahead and take the, and by the way, we can't use the series thing here because we don't have anything going to infinity, right? Okay, take the antiderivative. So the antiderivative will be 1/2 natural log 2x minus 1. Where'd the 1/2 come from? It came from when you do a little u sub. When you do a u sub, you're going to have a 1/2 du. That's a 1/2 du. We're undoing that 2 right there. Okay, we're trying to take this from 0.5 to 2. The 2 is fine, but the 0.5 is not fine. I'm going to call that a, and then take the limit as a goes to 1/2 or 0.5, specifically from its right. Okay, so if I now I'm going to put, first I'm going to begin by putting 2 in for x. We'll have 1/2. That 1/2 can come out totally. Natural log of 3 minus, now we're going to put a in for x and let a go to 1/2. Okay, if we let a go to 1/2, we're going to have this is going to 0. This is going to 0, right? And natural log, we know what the graph of natural log looks like. As x goes to 0, natural log is going to negative infinity. So this is going to negative infinity. This diverges. Okay, for this one, we have a vertical asymptote at x equals 0, right? Which is in our boundaries, so we have to consider that. The -1 and the 8, they're fine, but it passes through 0, so it passes over a vertical asymptote, so we need to consider that. Okay, I'm thinking of this as x to the -1/3. Thinking of that as x to the -1/3. So the antiderivative will be x to the 2/3 times 3/2. Okay? And I'd like to take, I cannot pass through 0, right? I should have written this as 2 different integrals. Let me come over here and write this as 2 different integrals. -1 to 0, and then 0 to 8. That takes care of those, that vertical asymptote. Okay, so now, I'm not really lined up, but that's okay. So we're from -1 to 0, but I don't want to put 0 because it's an asymptote. B is going to 0 though, specifically from its left, plus still 3/2 x to the 2/3. This time we're going from 0 to 8. The 8 this time is fine, but the 0, I'm going to write that as an a and let a go to 0, specifically from its right. Okay. Now put b in for x, let b go to 0. That's 0. Put -1 in for x. -1, the cube root of -1 is -1, but then we're squaring it, we're back to 1, so that's just a 1/2. I'm sorry, that's just a 3/2 here. Okay. Plus, put 8 in for x. Cube root of 8 is 2. 2 squared is 4. 4 reduces with the 2 to get 2, and then 2 times 3 is 6. Maybe you followed that. Maybe. Hopefully it's right. And then minus, now put a in for x, and let a go to 0, and that will be a 0. That would be your safe stop spot. Okay, this is not an integral. This is a second derivative, but this is a little review of something that we're going to need in a second. So, first of all, how do you take the derivative of this? The derivative will be, start at the top. If it's not just a plain x, you need to make sure you take this derivative and take it carefully. So take the derivative and write it down. And then you're multiplying by this function when you replace the t with 4x. We're replacing the t with 4x. So this will be 3 times 4x all squared, so 16x squared. Okay? I'm going to simplify that. That's squared. Okay? So that is g prime. And now we're going to take the derivative of that. When we take the derivative of that, we have the 4, right? We have the 4 that was out there. And then the derivative of natural log of u is u prime over u. So this would be 2 times 48 x divided by u, like that. That would be a safe stop spot. This reduces 12. Oh, this reduces just to 8 over x. That's nice. Okay. For number 14, I look at number 14 and I see arcsecant. I'm hoping you see arcsecant too, but that is arcsecant. The 2 can come totally out, right? The 2 can come out. But this is arcsecant. U is just x. A is 6. du is just a dx. So this is a fairly straightforward arcsecant. The 2 can come totally out. For arcsecant, we begin with 1 over a, arcsecant, and then we need the absolute value of u over a. That's that. Okay? And now we're going to number 15, because for 2020, you are not going to have anything like, you might have something like 13, but you're not going to have anything like these integrals. Why? Because in 2020 you have access to a calculator, and there are some calculators that can do this and spit it out to you. So this will not be on the 2020 test. Okay? So how are they going to find out, do you know how to integrate using some of these advanced integration techniques? And they need to have a way to test that where you cannot use your calculator. And this is one way that they could do it. I have no idea if they will do it, but this is one way that they can do it. So I made up this little problem. Okay? And these are not real easy to make up, but anyway, I think I managed to do it. All right, so here we're asked to, I didn't say find, but this should say find this integral, given that g is the integral from 2 to x of f of t, and here's the graph of f. Okay. Let's take a look at this. What I see here is a need to do by parts. I see x and I see some function of x, right? So I see that I can do by parts on this. So I'm going to come off to the side and do by parts on it. U is equal to x, so du is dx. dv is everything else. dv is everything else. So v is the integral of this. So if we integrate both sides here, we get v. The integral of g double prime is g prime. So now I'm going to come off here, come over here. uv is x g prime of x minus the integral of v du. g prime of x dx. Okay, now I need to put the 3 and the 5 where they go. Well, this I actually did, this should be evaluated from 3 to 5. This still has the integral, so I'm going to put the 3 and the 5 back on that integral. Okay? I'm going to leave this alone for a second and come over here. What is the integral from 3 to 5 of g prime? This is straightforward fundamental theorem of calculus. This is just g at 5 minus g at 3, fundamental theorem. Okay? So now, I need g prime, and I need g. This is going to be, let me go ahead and put this in. So this will be 5 g prime of 5 minus 3 g prime of 3, right? And this will be minus g of 5 plus g of 3. So I need g prime of 5, g prime of 3, g of 5, g of 3. I need all of those. Okay? So let's come off to the side and find those. First of all, let's come and find those. All right. First of all, if this is g of x, then g of 3 will be the integral from 2 to 3 of f of t, right? And we have the graph of f of t, so this is just area from 2 to 3. That's all it is. And the area from 2 to 3 here is that little triangle, so 1/2 base times height. The base is 1, the height is 2. So g of 3 is just 1 here. Okay, g of 5. G of 5 is the integral from 2 to 5 of f of t dt. Well, the integral from 2 to 5 will be this area here. It's above the x-axis, so it's positive. And that area is 1/2 base times height. So g of 5 is 3. Now what about g prime of 5 and g prime of 3? Well, here's g. G prime of x, we take the derivative of both sides, right? And the derivative of this integral is, the derivative of x is just 1, so it's just f of x. By the way, the derivative of 2 is just 0, so when you go, that's why the bottom boundary here, if it's just a constant, it does not factor into g prime at all. Okay? So g prime at 5, g prime of 5 is f of 5, and f of 5 is 0. It's just right there on the graph, f of 5. G prime of 3 is f of 3, and f of 3 is 2, right here. F of 3 is 2. So back over here, this is 5 times g prime of 5 minus 3 times g prime of 3 minus g of 5 plus g of 3. And that would be a safe stop spot. By the way, if you come over here and say what all of these values are, if you say what they all are, then this would be a safe stop spot right here, right? Because you've said what they all are over here. Okay, I know that's a little tricky. I made up another one for us to do, and I don't know why I wrote it so big. Let me see if I can zoom in a little bit so that we can actually see what we're doing. Okay. I don't know why I wrote that so big, but I did. Oh well. Okay. So there's a graph of, this time I called it the graph of G, just to change things up, not get too locked into where I have my f and where I have my g. And then I said that f is defined as this function, and I want to evaluate this integral. So if we want to evaluate that integral, which we do, I need to use by parts on that. So they're testing, this one problem will test by parts, it'll test fundamental theorem, both types of fundamental theorem, it'll test what you know about area under a curve and all of that. It tests a lot of concepts in this one problem. Okay, so I'm going to come off to the side, do a little by parts. So I'm going to let u be the x, let dv be everything else. So du is just dx, and v, the integral of this, would be f prime of x. So my integral will be uv, oops, I almost put u, x, f prime of x, from -2 to 2, minus the integral from -2 to 2 of v du. Just like that. So this is 2f prime of 2 minus a -2 f prime of -2 minus, okay, first fundamental theorem here, f of 2 minus f of -2, first fundamental theorem. Okay, so we have 2 f prime of 2 plus 2 f prime of -2 minus f of 2 plus f of -2. And now we need to evaluate each of these. So I'm going to come off to the side. Okay. First of all, let's do our plain f's. So f of, let's say f of, I don't care, f of 2. Let's do f of 2 first. So f of 2, we replace x with 2. And when you replace x with 2, you get -2 to 4 here, right? Okay, so I need the integral of g from -2 to 4. Well, -2 to 4, -2 to 4 would be all of this, right? -2 to 4 would be all of that. So I have a positive quarter circle of radius 1. So that's just pi over 4, 1/4 pi r squared. And then for the rest of this, I notice that these are the same areas, but one's on top and one's on the bottom, so that's just going to go away, right? I don't even need to consider that. So I just need this little piece here, and that will be, I'm making sure that, yeah, that will be 1/2 base times height, 1 times 3. Okay, f of -2, because we also need f of -2 down here. F of -2 will be the integral from -2 to, if I put -2 in for x, I get -4, right? So I need the integral from -2 to -4. -2 is right here, -4 is right here. So this is the area I need this time, right? So for this piece, since this is a straight line, this has to be, the y value is -1, 1, 2, this is 4, -1. So this is just half of a square, right? That's just half of a square. So that's negative 1/2 because it's below the x-axis, plus pi over 4, 1/4 pi r squared. So I got those two pieces. Now for f prime. For f prime of x, the derivative of this integral, don't forget to take the derivative of that 2x, 2, and then replace the t with 2x. So f prime of 2, which we need f prime of 2, will be 2g of 4, right? And g of 4 is negative 3. F prime of negative 2 will be 2g of negative 4, which will be 2 times g of negative 4 is negative 1. So f of negative 2 is negative 1. So if we come back here and replace everything, this will be 2 times f prime of 2 is negative 6. F prime of negative 2 is negative 2. F of 2 is pi over 4 plus 3/2. And f of negative 2 is negative 1/2 plus pi over 4. Just like that. And yes, you can simplify that, but we don't have to. Okay, so safe stop. In fact, this actually would be a safe stop spot because we came over here and said what each of those was. Right? Okay. When we are doing our practice test, I have some more like this for you. Okay? So I know that these are involved, but if we practice a few times, I think we'll be okay. And that's our review of integration. Let me know what questions you have.